This is Bob Capetta from the University of Illinois at Chicago, and this lesson is on absolute minimums and maximums. The extreme value theorem tells us that if we have a continuous function on a closed interval, then that function must achieve both an absolute max and an absolute min on that interval. So a point that is the highest, a point that is the lowest. There may be more than one, but we'll have at least one absolute max and at least one absolute min if we have a continuous function on a closed interval. So our process is to first identify all the critical points in that interval. Recall that a critical point is a point x where the first derivative is 0 or where the first derivative doesn't exist. We will use it again as long as it is within the range that we're given, within the interval. Now our candidates for absolute min and absolute max are those critical points we identified in step 1, as well as the endpoints. So we're going to test those values. So we evaluate the function at those critical points as well as the endpoints. The largest value that we see will be the absolute max, and the smallest value will be the absolute min. So we're going to give the function f of x is x squared minus 4x plus 1 on the interval from -1 to 6. Our first step is to identify critical values. So we're going to look at f prime of x, which is 2x minus 4, set that equal to 0. There is no point where the first derivative doesn't exist, but solving this equation we get 4 is 2x or x is 2. Now, is it a candidate? It will be as long as it's in the interval from -1 to 6, and sure enough, 2 is in that interval. So that will be a candidate. We will test 2, we will test -1, we will test 6 to see which one is the highest, which one is the lowest. We're going to plug the endpoints -1 and 6 together with the critical point in the range into our function f of x is x squared minus 4x minus 1. Plugging in -1, -1 squared is 1, minus 4 times -1 plus 4, plus 1, we get a value of 6. Plugging in 2, 2 squared minus 4 times 2 plus 1, 4 minus 8 plus 1, -4 plus 1, -3. And plugging in 6, 6 squared is 36, minus 4 times 6 minus 24 is 12, plus 1 is 13. The highest value will be the absolute max. So looking at our values, 6, -3, 13. 13 is the absolute max. Where does it occur? It occurs at x equals 6. The absolute min is the lowest value we see over here. Absolute min of -3, where does that occur? That occurs at 2. So that's our process. As long as we have a continuous function on a closed interval, we'll always have an absolute max and an absolute min. F of x is x squared minus 4x plus 1 is a polynomial. It's a parabola. It's always continuous. Of course, it's continuous on the closed interval from -1 to 6. Our next example is to find the absolute min and absolute max of the function f of x is -2x cubed minus 3x squared plus 12x plus 1 on the interval from -3 to 4. This again is a polynomial, continuous everywhere, so it's continuous on the interval from -3 to 4. Our first step is to find the critical points. To do that, we're going to take a derivative. -6x squared minus 6x plus 12. The derivative exists everywhere, so our only critical points will be where the derivative is 0. Factoring out a -6, -6x squared divided by -6 is x squared. -6x divided by -6 is plus x. 12 divided by -6 is minus 2. And then factoring this, that will give us x plus 2 times x minus 1 equals 0. -6 can't be 0, so either x plus 2 is 0 or x minus 1 is 0. We get critical values of x is -2 or x is 1. Are they in the interval? We are going from -3 to 4. -2 is between -3 and 4, and 1 is between -3 and 4. So our candidates for absolute mins and maxes will be our critical points and our endpoints. We'll test all of them. The highest value is the absolute max. The lowest value is the absolute min. And again, we use those because they're in that interval. So here we go. There's our function. There's our interval and our critical values. So we're testing -3 and 4, the endpoints. -2 and 1, the values in that interval, plugging them into -2x cubed minus 3x squared plus 12x plus 1. Plugging in -3, -2 times -3 cubed minus 3 times -3 squared plus 12 times -3 plus 1. We get -8. Good job for a calculator for that, of course. Plugging in negative 2, the result is negative 19. You can see how that was computed. Plugging in 1, we get 8, and plugging in 4, we get negative 127. We're going to first look for the absolute max. What is the highest number that we see here? Negative 8, negative 19, 8, negative 127. Absolute max of 8, where does it occur? At x equals 1. How about an absolute min? What's the lowest number we see? Negative 8, negative 19, 8, negative 127. Absolute min of negative 127 occurs at the endpoint of 4. Let's take a look at this question. Find the absolute min and absolute max of the function f of x is 5 plus the cube root of x minus 2 squared on the interval from 1 to 10. And indeed, this function is also continuous everywhere. We're going to go ahead and find the critical values, find the derivative, find values where the derivative does not exist or where the derivative equals 0. And if they are in the interval, we'll test those to see if we have the highest or lowest value. So how do we identify the critical points? We start with our function f, and let's rewrite that as 5 plus x minus 2 to the 2/3 power. And then let's take the derivative. The derivative of 5 is 0. The derivative of this piece will be 2/3 times x minus 2 to the 2/3 minus 1, using the power rule, times the derivative of the inside. But the derivative of the inside is just 1, so that's not an issue. 2/3 minus 1 is negative 1/3, which means 1 over x minus 2 to the 1/3. X minus 2 to the 1/3 is the cube root of x minus 2, so we have 2 upstairs, 3 times the cube root of x minus 2 downstairs. And normally speaking, we would take our first derivative and set it equal to 0, but that is never equal to 0. But there is a value x where the derivative doesn't exist. That, of course, is when x is 2. If we plug a 2 in to that derivative function, we get a division by 0, which of course is not something we can do. So again, there's our derivative, and that derivative is never equal to 0. But f prime of 2 does not exist. That is a point where the derivative doesn't exist. That is a critical value. Is it in our interval from 1 to 10? It sure is. So if that's the case, we're going to test 2, and we're going to test the endpoints from 1 to 10. Here's our function, here's our interval, there's our only critical point. We're going to test 1 and 10, the endpoints. Test 2, the critical point. So if we plug 1 in, 5 plus the cube root of 1 minus 2 squared. 1 minus 2 is negative 1. Squared is 1. Cube root of 1 is 1. 5 plus 1 is 6. If I plug in 2, 2 minus 2 is 0. 0 squared is 0. Cube root of 0 is 0. 5 plus 0 is 5. And then plug in 10. 10 minus 2 is 8. 8 squared is 64. The cube root of 64 is 4. 5 plus 4 is 9. Start with absolute max. What's the highest value we see? We have 6, 5, and 9. 9 is the highest value, so absolute max of 9 at x equals 10. And how about the minimum? Well, we have 6 and we have 5. Absolute min of 5 at x equals 2. Now, if we have a function that is always concave up, like a parabola, it will have an absolute minimum. And that absolute minimum will occur at a critical point. So to use this method, we have to convince ourselves that the second derivative is always positive, and then we can identify what that minimum will be. So our example here is f of x is 3x squared plus 2x minus 9 on the interval from negative infinity to infinity. There's our function. Our first derivative is 6x plus 2. Our second derivative is 6. If the second derivative is positive, the function is always concave up. Second derivative is always 6. Second derivative tells us if it's concave up, this function is always concave up. It will have a minimum at that critical point. So looking at that derivative, 6x plus 2, the derivative always exists. Set it equal to 0. Negative 2 is 6x. Negative 2/6 or negative 1/3 is x. That is our only critical point. That's got to be our absolute min. Now what is the value of the function? So we're going to go ahead and plug negative 1/3 into this function. 3 times negative 1/3 squared plus 2 times negative 1/3 minus 9. 3 times a ninth minus 2/3 minus 9. 3/9 is what? 1/3 minus 2/3 minus 9. So we get negative 1/3 minus 27/3 or negative 28/3. So this function has an absolute min of negative 28/3 at x equals negative 1/3 on the interval from negative infinity to infinity. That is indeed the lowest value this function ever attains. And similarly, if we want an absolute max, we need to have a function that is concave down forever. So we look at a parabola like this with a negative second derivative, always concave down. It will achieve an absolute max at its critical point. So our example here is f of x is negative 2x squared plus 24x plus 3. We want to find the absolute max on the interval from negative infinity to infinity. First derivative, negative 4x plus 24. Second derivative, negative 4. So it's always concave down. If it's always concave down, it will have an absolute max at the critical point. The critical point occurs where f prime is 0. Setting f prime equal to 0, we get 0 is negative 4x plus 24. 4x is 24, x is 6. So this function will have an absolute max at x equals 6. We just need to find out what that value is. So second derivative is negative. It's always concave down. Our critical value is x equals 6. Plugging 6 into the function, negative 2 times 6 squared plus 24 times 6 plus 3, we get 75. So this function achieves an absolute max of 75 at x equals 6. And that will conclude this lesson.